when you're around too. I'll try. There will be at least a short mental break when I pass out the notes for the next section. So, yet another chaotic beginning to my recording. So here, some of the questions I was asking you, do we have a hole? Do we not have a hole? We talked about if we were rotating around the same axis, we were touching the whole time, no hole, other ways. So let's go ahead and we're going to take one region here and we're going to rotate it around 3 different vertical lines. Notice we're the y-axis, x equals 4, x equals 6. All of those are vertical lines. If you're rotating around a vertical line for this method, you're going to be working in terms of y. Let me show you what this looks like. Oh, I was pulling up pictures of mathematicians earlier. Riemann and the most glorious eyebrows in the world. This is Gregory Perelman. He solved one of the Millennium Prize problems. So he got $1 million, but he was like, no, don't give me $1 million. I would like to go live in Russia with my mother. So then he just went back to Russia and did math. All right, so we're going to be rotating. That is my cap and gown spreadsheet. The square root of x equals 0, x equals 4. Let me scroll out a little bit. We're going to be rotating it about the line x equals 0, which is the y-axis. So just a little bit of a picture of what's going on here. Notice our rotation definitely does look different. We're kind of rotating horizontally instead of vertically. Do you think there's going to be a hole in the middle of this thing?
Yeah. No. Yep.
All right. If we think about the question, is our region touching the axis of rotation the entire time as we rotate around? Is it? Okay, let me go back and I'm going to pull this back. Nope, don't play. This is our axis of rotation, the vertical line. Is this region touching that the entire time? No, it's just touching at the very, very bottom, that kind of origin piece, but we'd want to see kind of the behavior if I rotate around this line. Notice that region's touching that line the entire time. We're not touching that guy. So we're definitely going to have a hole in this case, but we got to have a drawing. Let's sketch. So here is our little region. I've been labeling some of the y-axis, and since I said we were working in y, yeah, do you need notes? Cool. Anyone else need notes? As I've been labeling these, I've been usually labeling the y value as well. Seems like that might be a good idea since I'm going to be working in y this time. Any thoughts on the y value for the point 4 comma something? 2. Perfect. Square root of 4 is 2. We're working with the square root of x. Wonderful. All right. As I'm looking at this axis of rotation, this is our y-axis. Notice if I kind of draw those radius lines like I was last time, the big radius and the small radius, we do have distance between our axis and our smaller, kind of our closer curve. So we got 2 sets of pi r squareds. All right, that big radius. We want to do a top minus bottom. When we think about top, we want that to be to the right-hand side. Think of where our bigger x values are. What are your thoughts on top minus bottom? 4 minus 0, which I will eventually simplify to 4. If you want to be bold and simplify right away, you cool. Thoughts on the small radius? Ooh, okay. So I like that we're realizing we need to use the curve. I do like Emery from the back, if you heard him whispered, y squared. We want to work in terms of y here because we're going horizontally. So he's solving this in his head for x equals y squared. We're going to do y squared minus what? 0. We're going back to that axis. As I transition to my volume, just like last time, I'm going to factor out my pi. And I'm going to simplify a little bit as I go, thinking that I'm either going to integrate by hand or using the calculator. So I'm going to do 16 minus y to the 4th. This is probably an example of an integral that I could expect you to do by hand. It's not super difficult. You'll have some fifths, but we can deal. What am I missing? Thoughts? 0 to 2. If I'm working in terms of y, I do want to be going up and down. I want to be thinking y values, so that 2 that Ashley provided us with, great. Shall we rotate around something different? Yeah. So think of your functions. Notice this function is like x equals. This line is like x equals 4. So you're doing a function that is x equals something minus x equals something. So the variable, when we say in terms of, I mean like the letter that's in, like acting as my variable of integration. But just like when we do these like f of x minus g of x, that kind of looks like in our head like a y equals stuff with x's in it minus y equals stuff with x's in it. All right, an interesting kind of thing that's happening here, the 4 minus 0, I just want to give you some physical context for what's happening there. The 4 minus 0, if you see a constant radius like that, in your head, what should be happening? What do you notice? This is a very vague question. I'm hoping for a specific answer. What do you notice kind of about the outer edge of this thing?
Constant throughout.
Yeah, we have a constant radius. So you guys notice how the outside is like super cylindrical in nature? That's going to happen if we have a constant radius, because we don't need calculus to find the volume of a cylinder. We just have that constant outer part. So if you can kind of imagine some of these things, if you have cylindrical things, they should have constant radiuses, which is a kind of cool way to check your work. If you didn't find that cool, no worries. I usually find different things cool than most people nowadays. I know. I taught my AB class L'Hopital. They were like, okay. All right, let's change my line. I want to rotate around this now. Hole or no hole? No hole, says someone. Do you guys agree?
Yeah,
Checks out? Let's find out. Are we right? It looks like a cookie. A frisbee, yeah. Checks out. Be a pretty dense frisbee. All right, so no hole. That means one set of pi r squared. So a equals just pi r squared. I don't have to subtract anything because there's no kind of area I need to subtract out for that hole. My radius is looking like this guy right here. Thoughts on that radius? 4. I want to subtract something. Minus y squared. Now, we will talk about, a bunch of people in my other class said y squared minus 4, kind of a different direction of subtracting. That makes me a little uncomfortable because all the y's we're dealing with are less than 4, so that would technically give a negative radius. In this method, it doesn't really matter because we're squaring it, but in the method we'll start today called shell method, our variables will not be squared. So I always like to try to subtract in what I would consider the correct direction. You can check that by picking a y value. We've got y values between 0 and 2. Sorry if I said 0 and 4 before, I was looking at the x value. 0 and 2. So if I plugged one of those in, like it looks like I might have drawn mine at like y equals 1, I would get a positive radius here. Throwing in the volume. What am I missing? Thoughts? Same ones. I'm still going to do 0 to 2. Again, those are super region specific. We've kind of seen that as a theme the entire time. What that means for you is if you see a full Fourier response, which I'll probably put one on the Unit 7 test to be quite honest, because there's a lot of good examples. Even if I do area between two curves, cross sections, and rotation, even rotation both ways, find the bounds once, and unless you change your variable, you found the bounds for the whole question. All right, let's move this line one more time. X equals 6. Hole or no hole? Hole. Do you not like my questions? Okay. Sorry, whenever anyone laughs, I always think it's me. It's a really stressful thing to have as a teacher. All right, thoughts on big radius? All right, start with 6. Okay, so that's here. Minus y squared. So you guys were correct. Those of you whispering about y squared, that one is involved in our biggest radius there. Thoughts on the small radius? 6 minus 4. So that means to me, that's a constant radius right there. We have a radius of 2. So if I look at this picture, which we'll do in a second because they're kind of fun to look at, if I move this, I think I should see like a cylindrical hole happening in the middle. Does it look like that'll happen?
Yeah.
Yeah. Kind of looks like you took a big cookie, took a cookie cutter and punched out the middle of it. Yeah, so if it's a constant, you should see that kind of cylindrical happening there. Yeah.
Can you go back to your picture when you're like drawing?
Would love to. Thoughts?
Wait, can you like draw the line? Like this one where there's like a long line.
Yeah, let me redraw a little bit below, just so it's easier to see. All right, so R6 is over here. So my big radius is going from this axis all the way back to the curve part of it. And then the small one is going from the axis back to that vertical line. And you can draw those lines anywhere. Just to really be clear, I'm just drawing them anywhere in my region. I'm not using like a specific place. Nope, because we're not rotating that guy. We're rotating this region around this line. So other than touching the y-axis at that one origin point, y-axis doesn't really count. All right. Yeah. No. Keep going. For the purple one? So for that one, we were touching the axis of rotation the entire time, so we didn't have a hole. You could do like a 4 minus 4 if you really wanted to have like a small radius every time, but you're not going to have a hole in that one. All right, as I factor the pi out, you guys still think 0 to 2 for the bounds? I do. This is a good example of an integral. Let's see, that's 2 squared is 4. That I probably would not expect you to be able to do. Ooh, I missed a squared there. So I added a squared here if you were copying down my notes. Both of these guys would require some foiling. Those are probably outside the scope of at least this test. The AP test might expect you to be able to do that, but I certainly probably wouldn't expect you to do that by hand because you're foiling out. You'd have probably thirds and fifths once you start integrating. That's just a lot of gross math that isn't really necessary for this type of stuff. So what I want to show you next, we're actually going to be done with these notes right now because we're going to hit one of the questions on this set of notes with the next set. Is I want to talk about, well, what if I hate working in Y? What if I want to be able to work in X no matter what? Or I have some sort of equation like this, y equals square root of X. We were super easily able to solve it and get it in terms of Y. What if I couldn't do that and I were forced to work in X? So we're going to find a way to rotate parallel to our axis. That's pretty darn cool. So if you need like a brain break, this is it.
Grab a drink.
Yeah, I'll go ahead and put a timer for 4. Take a break.
Thank you. Thank you, Miss Evans.
Okay.
Yeah, we're like behind. Big question is finding friction and then slide is good. Honestly, it was easy.
No,
The physics test?
the multiple choice was so hard. The other part wasn't
Three
so bad.
responses, multiple choice was easy.
No, the free response was just like the review sheet. So it was okay.
I'm in water, I guess.
The first thing question at the end was hard.
Oh, that one, yeah, that one I didn't get.
Yeah.
I didn't do this one. I looked at it and I was like, yeah.
Does it say y is bounded by y and x?
So the y equals 0, if you look at this picture, if I didn't say bounded by y equals 0, this region could technically just keep going down forever.
Okay.
So think of it like you're fencing in a yard for like a dog. If you don't have fence around one part, it can just keep going, and that's no good.
Miss the no says he will order his I didn't. I don't even know.
Did you feel like it?
Probably.
93 passes. With the grain, across the grain, and against the grain.
Yeah, aren't you, because you went gold enough to reject traditional gender growth colors?
Yeah.
Yeah, I do.
I think you like the white.
Like this happening down.
Oh, well, the other way.
Yeah.
I need to get my senior year sheet.
Oh,
Merch.
I didn't set a timer.
Oh, well. I'm like almost. I don't know. I think anything. It's all up here, baby. Kidding. I get my grades.
I meant to actually go and pull all of these pieces out and reveal my class.
Thank you.
Oh my god, I went from 58. Hi.
Yo, that's sick. Yeah, wear that
If you go on our Zoom page, there is a link on the material if you want that. Or this weekend, I'm gonna be sending out emails to like everyone's parents. And you can also do that.
Okay, perfect. Thank you.
Can we be ready to go now? I didn't set my timer. I forgot. All right. What if we wanted to rotate differently? As I put your test back on my desk, we're going to talk about something called shell method. Now, shell, I don't want you to think of like I am Moana on a beach. What? Oh. What a terrible person I am. All right, what's the first function that's on there? X minus x cubed. Found the first example. Whoa. Why does it look like that? Oh, because I can't go this far. Bottom of the first page, bud.
Oh, X minus X.
We're gonna-
focused on the volume. I was like, what?
I gave a really All right, so I'm going to show you kind of what's going on here. This is the first example, but I'm going to take the rotation, and I'm just going to show you like a little sliver of it. I actually might make it even smaller than that. Let's do that. So this is going to show you an example of what the shape looks like that we're going to be rotating. So we've been creating like discs or discs with holes in them that get called washers. What I want you to think of these shapes as, if you've ever seen, hopefully you have, like a canned food item, you know the label that goes around it? That's what I'm talking about when I say shell. So kind of watch when you play the wrong thing. I'm so disappointed in myself right now. All right, so I'm gonna let this rotate. Can you kind of see what shape I'm talking about here? Okay, so benefits to this shape. Most of the questions you're going to do for the AP test will be able to be done with washer or with shell method. There's very few that have to be done with shell method. This is actually one of them, and we'll talk about why. But benefits of this shape, one, it already has a hole in the middle. So we can remedy kind of having the space in the middle of our shape a lot easier. It'll actually work with the bounds of our question instead of having to deal with like an entire other shape, an entire other circle. Also, we get the benefit of if we're going around a vertical axis, we could stay in terms of X. I don't know about you guys, but my brain just works better in terms of X than it does in terms of Y. So a lot of these questions where we're rotating around a vertical axis, I can get around having to translate everything into Y. That being said, we'll do this both in terms of X and in terms of Y, and you'll kind of see the differences. So let's talk about this shape first, and then we'll keep going. So first of all, we need a new volume or a new area formula. We can't use pi r squared anymore because that's not a circle anymore. So I'm going to draw some pictures. What was that noise? So think of that as being like an infinitely small, thin cylinder. So that's why I like the comparison to like a label for something, because we're thinking that that's like infinitely small, kind of like our discs would be infinitely thin from disc and washer. This guy is super infinitely kind of thin, like a piece of paper, and we're going to layer them on top of each other. So kind of that's how we're building this up. Let's say I cut this though. This is going to help us get our area formula. If I cut that, what shape is it going to be? So like here's the cylinder. I cut it, it's a rectangle, right? Master of props. What? Yeah, if I unwrapped it, it would be a rectangle, right? I say that because I know how to find the area of a rectangle a lot more than I know how to find like the lateral surface area of a cylinder. All right, I'm gonna argue that's h tall, h meaning height. Question, how long is it? All right, do you agree with me that if I take this, what shape is the top of a cylinder? Circle. If I unwrap that, it still has to do with the circle, right? What word is that? That's a circle word. I want a different circle word. Circumference is the word. Do you agree with me that the top of that rectangle is if you took a little man and you walked him around that circle? What's the formula for circumference? 2 pi r. So if you looked at these formulas up here, you're going to notice we have 2 pi r h. The 2 pi is coming from the circumference, the r also from circumference, the h is coming from the height. One thing I want you to notice, kind of like I just mentioned while we were finishing up our washer method, the direction of your subtraction matters a lot more in this method because nothing is squared. So while in disc and washer, I could get a little willy-nilly with the way I was subtracting. Here, the direction of my subtraction is going to matter a lot. I will say the height is going to feel very normal to us of how to find that. That's going to be a pretty straight top minus bottom situation like we've been doing this whole time. The radius is a little weird, so if you're going to choose a place to focus on our discussion today, I would focus on when we're talking about the radius. So let's draw some pictures, get an idea of what's going on. I'm just drawing two random functions that intersect in two places, and that kind of look pretty. Yours can look different. It's okay. I'm going to draw my axis of rotation, and notice now, unlike what we were doing with disc and washer, we're going to be rotating parallel to our axis of rotation. So if I'm working in X, I'm actually going to have a vertical line. That's different than the disc and washer. It's exactly the opposite. Okay, this is going to be our height. Notice that's kind of a top minus bottom with our two functions. So that's going to feel super normal. The radius, though, I'm going to kind of draw this cylinder in. I probably won't draw this very often because it does get a little confusing to look at. But if you're trying to draw that cylinder, it's kind of centered on the axis, and then it goes out to whatever x value you're currently at as you're taking the integral. So if you were drawing a line for that radius, you could kind of draw it from the axis out to where that height is. Sometimes I'll draw it at a right angle like that, or sometimes I'll make a little T. I'll show you all the things that I do to help myself out. Yep, so from that height line, wherever you drew that, remember that changes, so I'm just doing it somewhere in there.
From the height to the thing you're rotating is your radius.
Yeah, so really what I want you to notice right now, and we'll talk a lot more about this radius, because it is the weirder part. What I do want you to notice right now with this picture is that the axis of rotation is going to be at play for that radius. Okay? Same thing if I choose to draw over here. Let's draw something more interesting. Let's draw something like this. We just did one that looked like that. If I'm going a horizontal axis of rotation, notice I'm again rotating parallel to this region. So my height is parallel to that guy. Again, I could draw this, kind of trying to draw it so it's centered on that axis of rotation. And sometimes I'll draw by radius just farther down. You can draw it in that circle or outside that circle. But we're talking between that height line, which we'll talk about how we get that distance. But we're also talking about that axis of rotation. So again, key point right now, the axis of rotation is going to be at play for the radius part. So things that I'm kind of noticing, we're going to structure the notes just like we did before, where I'm going to take one region and rotate it around multiple lines to kind of see what changes. The thing I'm predicting right now is that the radius is going to change a lot depending on the axis of rotation, but some of the other stuff doesn't seem to be quite as dependent on that axis. Yeah. Mm-hmm. So the bounds are going to be very dependent on whatever letter we're using. So kind of like before, if we're using x's in our integral, we want to use x values for our bounds. Y's in our integral, we're going to want to use y values as our bounds. And just like before, those bounds are always going to be really region specific, so it's going to be pretty easy to see. Promise. All right, so let's talk. I would love to get through kind of just this first part, and if we have to do the y's next time, we can do the y's next time, but just to get you a difference between these regions. Let's talk about first why shell method would be a good choice for these first few questions. So for this one, we're taking this region here, that's the one that I just showed you on Desmos, and we're going to rotate it around the y-axis, so this up and down vertical line. A couple of reasons why that I'm going to want to work in the letter X. First of all, if I even tried to just draw the radiuses, I'm going to erase those in a second, but if I just tried to draw the radiuses like before, I noticed that this curve has to do with both the top and the bottom radius, which is a little creepy and weird. If I'm thinking of top minus bottom, it would be weird to take that curve minus 0 and that curve minus 0. But also think about, we would have to be working in terms of y, because those lines that I just drew were horizontal. Can anyone think of a way to get this function in terms of x equals y stuff? Do you know how to solve that equation for x? We could factor it, but then we'd still have like an x and an x squared. We wouldn't want x equals something with x's and y's in it. I don't know how to solve that equation for x. So I'm pretty sure you don't either, unless you're very, very good at math, in which case teach me. But that is not an equation that would be easily solved or possibly solved for x. So we're going to want to work with this equation in terms of x in our integral. which means we need an up and down line. We need to be working in terms of x, where our function looks like this, looks like y equals stuff with x's in it. So in this case, we are forced to use shell method for any vertical line. So for our first one, I'm going to kind of draw some of these now, but the lines I'm really interested in, maybe let me draw them in a darker blue so you can see them. So that is cool if you want to draw that. Kind of your non-negotiable lines that I would love for you to draw are these two. I want to see the R and the H so you can investigate what those distances are. Now keep in mind that these things are getting kind of stacked along each other. So this is kind of just an example of one of the shells, but there's going to be a lot of them stacked on top of each other. That's going to get kind of curious and interesting as we set this up. So 2 pi r h. If we use shell method, that's our formula for our area. I want to start with the h because I think it's easier. Looking at h, we're thinking of our top minus bottom. Does anyone think they know what I'm going to write down for h? All right, I like the -0, but that height is changing depending on where I am in the region. So while it might look like 1 here, I want to use that function. So x minus x cubed minus 0. Again, that's because as I change my location, I'm drawing like a representative one, but as I roll throughout this region, it's going to change height. So I do want some x's in there. Yes. What do you want to do to it? You could factor out an x if you wanted to, but I think that in this case, since I'd probably be plugging this into the calculator, probably not helpful. Are you asking if I can make it like negative x squared or something? No. You can factor it. You could do this. I think you're getting confused between that and this. Better? Okay, cool. Our brains are tired, I know. It's Friday, we just did round 2. Right. So if you did, the problem with trying to solve for this is even if you divided by this, you get x equals something with x's and y's in it, which isn't helpful for our integrating purposes because we would need just in terms of one variable. All right, let's talk radius. So like I said, we're drawing kind of a representative guy here. We're drawing a representative shell. This shell moves back and forth depending on what the x value is for our specific shell that we're drawing. So what I would like to say is that this distance right here is the x distance of our current shell. It's whatever x value we're currently using for our shell. So like I kind of have in this picture right here. Notice that these A and these B's, that's giving the x value of where I currently am. So if this were infinitesimally small, like I'm drawing, this x equals 0.6 would be the radius of that shell. Or if I did A equals 0.7, that x distance is currently the radius of my shell. So wherever that x value is how big the radius is for my guy. If you are more interested in kind of a formula for that, I've written one down. It's kind of the top minus bottom with your variable of integration. So in this case, your x and your axis of rotation. So your x minus 0. The reason we have to use x there is as we go between our regions, so between x equals 0 and x equals 1, those radiuses are going to be getting bigger as we keep layering these shells around each other. So you have x and then back to that axis of rotation. As we move to our volume, I'm going to factor out that 2 pi and kind of simplify as I go. This will be a pretty good example of something I could ask you to integrate by hand, just because distributing that x isn't too terrible as far as the integration goes. Last choice, bounds, thoughts on them? 0 to 1. So going back to Gribben's question, he was asking, how do I know which bounds to use, the x bounds or the y bounds? Notice my integral has x's in it, so I want to use x values as my bounds. You can also do that trick of your pencil. You just want to lay it on the height. I can go this way to get to 0, that way to get to 1. So definitely a different look than we've done before, but a lot of the same concepts. Yeah. Like an x equals -1. Let's do it now. Great segue. Yeah, so what I want to show you now, and hopefully we'll kind of get this done before we leave. I would love to do just the next 2 at least to show you what happens if I move my axis to the left of my region, what happens if I move my axis to the right of the region. So let's start with left. I missed it. Okay. I'm actually going to use the same height because that's still in my region. You think my radius is going to get bigger or smaller?
Wait, is
We don't count negatives though, right?
So I can put my axis in the negative area. Let's not rely on my drawings. Let's rely on Desimos. All right. So here is rotate around x equals 0. Here's a representative shell. So I can make it bigger. So that guy's rolling around that way.
That's what we just did.
This is what we just did.
Okay.
If you watch the whole shape go, that was going from 0 to 1. So here's the whole shape going. So what I'm going to take is I'm going to take the same region, but I'm going to push the axis farther away from it. So let me not give away everything. I'm going to move the axis over there. So if I asked you the question, hole or no hole?
Oh.
Definitely. All right. Is that radius, though, getting bigger or smaller? Bigger. And it becomes more obvious when I move this back to the kind of small little section that I was doing. Notice here, I'm still working with these shells. We're just layering them on top of each other as we go. This guy is a much bigger cylinder. And the nice part is our radius is going to take care of the fact that there's a hole in there. So let's try to set this up, get our brains working. So if you wanted to draw this, you want to kind of try to draw a flat circle guy with its center at your axis of rotation. Again, you don't necessarily have to draw that if you don't want to. The lines that you're going to want to definitely draw are this height line and this radius line. So notice our radius, our distance between where I drew that height line and where I'm going back to the axis of rotation, that radius is a lot bigger. No, it's somewhere to the height line. So if you want to make it like a T, you could. All right, shell method, still 2 pi RH. Is my height changing? No. That, in this case, is going to be pretty region specific since we're talking about the height within that region. The radius is the big part that's going to change if we're working with our shell method. Anyone have a thought on how big that radius is going to be? What would you put down for that radius? X plus 1. Now, there's a couple of ways to think about that. If you want a rule, you can take your variable, which is x, that's this distance right here that we said before, and we can subtract the axis of rotation. So we could do x minus -1. If you're just looking for a rule, great. If you're looking for kind of a physical explanation of why that is, You're taking that x distance that we talked about before, and you're adding the distance between your axis and the old axis that we had. So you're taking x and adding another 1 to it, that constant 1 in the middle. All right, let's go ahead and fix this guy. So now I have x plus 1 in here, and I've got x minus x cubed. I'd have to FOIL that out, so probably a calculator question. What are your thoughts on bounds? 0 to 1. Now notice, we actually don't have to do anything fancy to fix the hole, because our closest point to that axis, that x equals 0, if I plug that in, it already has a radius of 1, so it's already kind of fixing that hole, and we don't have to go in and physically fix that ourselves with our math. Yeah, so options for radius. You can either think of, I want to take my variable of integration, which is wherever I drew my height line, and subtract my axis of rotation. So you could do x, because we're working in x, minus -1. If you like rules, that's a good rule. If you want to think distance-wise, wherever you draw this is x away from the y-axis, and then I need to add the extra 1 distance there. All right, one more line, and then maybe I'll shut up for today. Real, like, please shut up. I know, me too. From crushing the test. Oh, rushing the test. Okay. All right, just for the sake of argument, I'm going to draw my height at a different place because it doesn't really matter where you draw it. Let's make this a skinny boy. Oh, I made the side of that really weird looking. Sorry, let me try that again. Like round 5 on my drawing. Yeah, so if you don't like drawing the cylinder, you can draw just this if you want. I kind of think this one's a little harder to see than disc and washer because radiuses, I don't know, they're just a little easier. So you could draw that radius there, or you could draw it a little bit closer. You could draw it like a T if you wanted to, but those are the 2 distances you're wanting. And I shouldn't label that H because that's R. All right, let's do this thing. 2 pi. All right, even if I draw my H elsewhere, is it gonna change? No, it's still that top function minus that bottom function in that region. So we're still working with x minus x cubed down to the x-axis. What are your thoughts on the radius? I almost agree. Other way. I'm going to do 2 minus x.
Oh, because it's bigger.
Yep, 2 is bigger than wherever I'm drawing that line. What you can do is you can choose an x value within your region to plug in. So these x values are between 0 and 1. So let's say I chose the 1 there. If I do 2 minus x, I would get 2 minus 1 or 1. That's what I would expect the radius to be there. If I accidentally subtracted the wrong way, I would get a negative number. I could be like, oh, that makes sense. Another way to kind of distance that to yourself, this whole distance right here is 2, and we want to take away the distance that we're calling x, so that's another way to justify that 2 minus x there. I like to give both examples because I think it makes sense both ways, so choose whichever one makes sense in your brain. Bounds changing or no? No, very region specific. All right, let's just finish out this problem by talking about this very last thing, and then I promise I will actually shut up. If I take this region, but then instead rotate it around a horizontal line, what do you think is going to happen? All right, didn't we say I have to work in terms of x here? So I have to have this. And you're trying to make a point and you erase what you're writing. So I have to have my line going up and down if I want to work in terms of x. That's not parallel to my axis. So I can't use shell method. What could I use instead? Washer. Even easier. Is there a hole? No, I could use disk method. So I could use pi r squared. Let's just make sure we remember how to do that. What's top minus bottom for my radius? Down to the x-axis or 0. Here, we'd be only factoring out a singular pi. Would my bounds still be 0 and 1? Yep, those are still the x values I'm working with. And I could be dx. Okay? So one of the tough pieces, and one thing I am going to encourage you to do either over the weekend or next time, whenever you start working on your problem set, most of the questions I give you are going to be ones where you can do them both ways. So it's kind of interesting to see what your preferences are. Sometimes I have people whose preferences to just, I'm gonna work in washer method until it's physically impossible to work in washer method. Some people are like, I'm gonna work in terms of X until it's physically impossible to work in terms of X. You can kind of decide which person you are. Nate. Scenario. So for this one, if I were going around any of these vertical lines and I tried to use discard washer, I'd have to be working in terms of Y. I can't do that for this function. We're going to talk about this one too, where if I try to set my line up vertically, I'd have kind of two different situations. One where this is my top, one where that's my top. So I'd have to break the two different integrals. That doesn't sound fun, so I'm going to try to work horizontally instead. So it's kind of sometimes the picture, sometimes the function. Usually you're going to be able to tell if you're trying to do something that doesn't work out. Yes, ma'am. Are you going to give me that piece of paper?
Yeah.
You trust me?
Yeah.
All right. Cool. I will get it to
I
whoever.
wrote Jordan Cheshire, and I don't know if she's turned in hers, but she
I have
like
no idea.
emailed the same principal, Kirsten, and Kirsten replied
Okay.
saying like,
Sounds good.
all right.
Yep, I'm sure the team will get back to you if they need like any